So welcome back, Level 2 physicists. Today we're looking at the conservation of momentum as part of our mechanics course. So what is momentum? Essentially, it's inertia in motion. Okay, so an object that is moving wants to stay moving. So in terms of these two objects here, which has more momentum? It will be the top one. And why? Because it has a larger mass, 2,000 or 20,000 kilograms compared to the 2 kilograms of the Tonka truck. In this example here, which one has more momentum? It's going to be, again, the top one because it has more velocity. Okay, 35 compared to 10, even though the masses are the same. So this is the concept of momentum. Momentum is essentially mass times velocity. The symbol for momentum is capital P. Mass is m and velocity is v, which you should know already. And the units of momentum are kilograms, meters per second. Okay, because you're going to be multiplying mass in kilograms by velocity in meters per second. Okay, so we also have the conservation of momentum principle. So it means that the total momentum of a system is constant. What does that mean? Well, it means that the momentum at the beginning, the initial momentum, will equal the momentum at the end of a collision, essentially, or the final momentum. Okay, so for the first example, which is known as an explosion, the sum of the momentums is going to be equal to 0, which means the sum of the momentums after the collision, once the ball has been released, is also going to be 0. And the second example, which is known as the hit and bounce, then the momentum, again, at the start, which is based essentially around the momentum of the ball hitting the skateboarder, will equal the momentum at the end. And you'll see from the arrows that the velocity of both the ball and the skateboarder are reduced. And the final one, which is known as the hit and stick, is again the momentum at the beginning will equal the momentum at the end of the collision, and you'll see that the momentum, the velocity of the skateboarder has increased slightly from 0, and the velocity of the ball is now 0. Okay, so in all cases, the initial velocity and the initial momentum, actually in all cases, initial momentum at least, will equal the final momentum. So we also have to consider Newton's third law. We've looked at the first and second law in some detail. And what Newton's third law says that for every action, there is an equal and opposite reaction. Okay, in terms of forces at least. Okay, so looking at the first one here, a person walks off a boat. There will be an action force forward, and the boat will have a reaction force backward, equal and opposite. Second example is a box on a table. There'll be a reaction force which is equal and opposite to the weight force of the box and the table. And the ghost skateboarder on the extreme right there, you've got the ghost skateboarder pushing against the wall, and there'll be the wall pushing back against the skateboarder in an equal and opposite fashion. Okay, so thinking about that, while driving down the road, a blowfly strikes the windshield of this particular bus, splats on the front of the windscreen. This is a clear case of Newton's third law, because the blowfly has hit the bus, and the bus has hit the blowfly. Okay, which two forces are greater? The force on the blowfly or the force on the bus? Okay, well, according to Newton's third law, they shall be the same. Now, there's a disparity of mass, which means that there's not much of an effect on the bus compared to the blowfly, but the forces will be equal and opposite, kind of counterintuitive in many ways. Okay, you also see this in projectiles. Okay, so if a cannonball is fired out of a cannon at a certain velocity, then the cannon is also going to go backwards at a certain velocity as well, and that will be equal and opposite in terms of that force. Okay, So that's known as the recoil. Okay, so, and you can see that there with the cannonball has a certain small mass. So that means it shoots out with a large velocity. The cannonball, the cannon itself is a larger mass, so that velocity, that recoil back, is a little bit smaller. And finally, just to summarize, another concept which you don't really touch on much in level 2, but you might touch on in level 3, is the idea of elastic and inelastic collisions. So in an elastic collision, the energy, kinetic energy, is conserved. And we'll look at energy in a bit more detail next week. And in an inelastic collision, kinetic energy is not conserved. Okay, so that is basically the concept of conservation of momentum. And now we're going to try and later link it to the conservation of energy.